Okay, my name is Filippo Berto. I work at the University of Padua. The title of my presentation is Multiaxial fatigue strength of top-notch specimens made of titanium. I would like to say that this work was started under the supervision of Professor Paolo Lazzarin, who was my supervisor and under my PhD, and also my chief when I worked at the University of Padua. And he is in collaboration with the last PhD student of Professor Lazzarin, Alberto Campagnolo. Dealing with multiaxial fatigue, we have different well-known criteria, very famous and applicable to different kind of components. I have summarized here the most known, but I have probably forgotten other criteria. And also there are some recent publications by Carpinteri, Santos, Freitas, and other authors that have shown the possibility to have a fatigue assessment under multiaxial loading condition under different combination of loads. And in particular, I would like to mention these five contributions. The first due to Andrea Carpinteri, the second due to Ali Fatemi, very recent, and another one very interesting by Professor De Freitas. Adding this, there are also two very important contributions, in my opinion, that are due to Professor Tanaka, who has shown that there are some cases where the drug propagation is very important, and we have an increase of the fatigue life studying non-specimen in comparison with the plain specimen. It is a very strange phenomenon called notch hardening, which is very well explained in these two papers. Dealing with open problem in multiaxial fatigue and dealing with our main topics of research, this is which is also the aim of this presentation, is the study of sharp notches, and in particular with the notch tip radius equal or tending to zero. Another important aspect is how to take into account the non-proportionality for this kind of sharp notches, and for this kind of geometries, always as discussed by Professor Tanaka, we have nonlinear effects, shifting effect in particular under torsion loading, and when we have a nominal load ratio equal to R-1. For our particular criterion, which is the strain energy density, so I'm a bit sorry to present the criterion based on the strain energy density after the words of Professor Sossi, but anyway I will try. There are different critical radii for us under tension and under torsion. Dealing with the strain energy density, we have also some good contribution, in particular by the first to use the criterion was Guillemot in 1965. Previously, an Italian researcher, Beltrami, proposed the total strain energy density as fracture assessment parameter, and later there are very important contributions due to Rinka and Pak and Nelson later. Dealing with the advantages of the local energy approach based on MCIF, we can mention different advantages. I know that there are also different drawbacks of this approach, and I will discuss also these drawbacks. The strain energy density allows to consider automatically the scale effect of a component and permits consideration of different modes. For example, as we do in this paper, consider the combination mode 1 and mode 3, permits consideration of the effect of the nominal load ratio. You will see how to do this. And in some cases overcome the complex problems tied to different non-stress intensity factor units when we are comparing crack initiation or root initiation, for example, when we are considering a welded joints, but also this is valid when we are comparing different kind of notches. And in some cases overcomes the complex problem of multi-crack initiation and their interaction. This sentence is valid only if we are thinking to a criterion for the fatigue assessment, not if we want to study the path propagation of the cracks. Set can be calculated with coarse mesh, and this is a strong advantage with if we compare the method with the notch stress intensity factor, which requires a fine mesh for the calculation, it directly can take into account the T-stress if we consider a volume of material able to capture also this effect. And in three-dimensional problem, it is able to consider, it is able to take into account constraint effect combined with three-dimensional effect, and so couplet mode we have discussed in the previous workshop dealing with fatigue crack propagation. And there is a direct link with other local approaches as discussed in the previous workshop, and where we discussed, for example, the link with the fixed stress criterion. Dealing with the analytical background, I don't want to bore you too much with this part, but the strain energy density has the advantage that it can be calculated take into account the nominal load ratio with the parameter called CW, introduced by Altaviso, Siemens and Bardi in 2004. This parameter is equal to 1 when we are considering an external nominal load ratio equal to 0, and 0.5 when we are considering a nominal load ratio equals to -1. Dealing with the strain energy density, our criterion is based on the definition of a control volume around the notch tip or shaft crack, and what we do is to average the strain energy density inside the volume, considering all the components. After simple calculation, we arrive to the last equation reported in the slide, where we can express the strain energy density, the average strain energy density, as a function of the notch stress intensity factor of mode 1 and the notch stress intensity factor of mode 2, when we are considering in plane shear stress. And it is easy to evaluate the range of the stress intensity factor considering the range of the notch stress intensity factor. In particular, we have some simple equation which provides the shape function A1 and A2, which are linked to the notch opening angle as a function also of the Poisson's ratio. These equations are valid only for the Poisson's ratio equal to 0.3. And extending the criterion to multiaxial fatigue, we can introduce in the equation also mode 3 loading. And in the case considering the present work, we have only mode 1 and mode 3. And we have a simple table which reports for each notch opening angle the value of E1, E2, and E3, which permits to apply directly the equation. The problem I would like to discuss today is that under tension and torsion combined, usually we have a problem with this criterion because we have different critical radius for mode 1 and mode 3 loading. And an example is shown when we discuss the data of the present research program. In particular, we can say that the experimental validation reports in this work consider the actual fatigue behavior of this titanium alloy grade 5 under combined tensile and torsion loading, both in phase and out of phase. We have considered plane specimens, torsion and tensile fatigue test, and also combined tensile torsion fatigue test on notch specimen, very sharp specimen with the notch radius minus less than 0.1 millimeter. Now I will show the imaging of the specimen, and we would like to show if it is possible to consider to reach a good final synthesis by using the strain energy density. The synthesis of the data from titanium alloys are reported here. We have considered this kind of specimens, a plane specimen and a notch specimen with a notch opening angle equal to 90 degrees and the notch tip radius very small, less than 0.1 millimeter. This is an image of the notch radius. This is a typical measure of our radius. And after that, we have collected data for the different case of loading, and in particular, we have considered the tension, the poor tension and poor torsion cases with a notch specimen and big notch specimens. After that, we have changed, for example, under torsion, the load ratio from -3 to 0.5, and we have seen that there is a very strong effect of this nominal load ratio also under torsion loading for this material. And we have considered multi-axial fatigue test, where we have combined tension and torsion in combination with the axiality ratio, which is the ratio between shear stress and tensile stress equal to 0.6. And these are the data with very large scatter and different behavior under different mode combination. We have summarized all the data. What it is interesting to understand is that for this material, the effect of out-of-phase loading is quite limited. And in fact, if we compare the two cases of R-1 and R equal to 0, we have almost the same fatigue strength in both cases. There is not a strong influence or reduction due to out-of-phase loading. And after that, we have also considered the fracture surface of the specimen to show if there were some possible differences between in-phase or out-of-phase fracture surface. Yes, we have found some different behavior. For example, here there is some fretting fatigue or a kind of the specimen seemed to produce a kind of debris during the test, but finally this different behavior does not provoke a very strong reduction in out-of-phase loading. The same for the same happens for the other load ratio considered. We have not a strong difference between in-phase and out-of-phase loading. And we have applied our criterion to this material, considering the equation I have shown before. And in particular, for plain specimen, we use directly the Beltrami expression, and for UNNOTCHED specimen, we use the strain energy density in the control volume. Before to apply the criterion, we have to evaluate the critical radius for the two materials. And what we have found is that the two materials have very different critical radius. These critical radius are linked to the critical stress intensity factor under mode 1 and mode 3 loading, and this information derived directly from sharp notches. And this information is the stress range of plain specimens. So this information comes from unnotched specimens. As always we do when apply the strain energy density, we compare the strain energy density of very severe notches and on the other hand the strain energy density of a plain specimen. To evaluate the critical radius, we have to equate the two equations, which comes from two information: the information from sharp notches and the information from unnotched material. All the analyses are made under a linear elastic hypothesis, so I can also obtain some simplified expression to express delta K as a function of, for example, the notch depth of the specimen, according to some useful expression proposed in 1998 by Professor Tov and Lazzarini. And again, I'm able to calculate the two sides of the volumes. It is also important to show that for our geometries, the critical radius, which is equal to approximately 0.8 millimeter, is inside almost the linear elastic zone for the considered geometry. Applying the criterion, we can summarize. We were able to summarize all the data from notched materials inside the scatter band. We have almost 90 data from different combination of loading. This is the synthesis only of the notched materials, and the scatter band is in terms of the strain energy density is 2.2, so it is very good compared. If we want to obtain a stress scatter, we have to make the square root of this value, so it is a very low value. And considering all the data all together, we have approximately 160 new results with a scatter band which is equal, if we convert in terms of stresses, it is equal almost to 1.6, which is comparable with IVAC scatter bands for usual fatigue. In conclusion, I have to say that we have considered a different combination of load for titanium alloys. The nominal load ratio was found to have a great influence on the fatigue strength and the phase angle seems to be, the effect of phase angle seems to be very limited. The reanalysis of the fatigue data in terms of the strain energy density range at the notch tip allowed to summarize the data inside the scatter band. We have a problem with the definition of the control volume. Under linear, if we consider linear elastic hypothesis, we have two different control radius for tension and for torsion. This is a possible problem. Our criterion is not able to keep into account the out-of-phase effect, because in this case the material is not sensitive to the out-of-phase loading, but if we have a strong effect due to out-of-phase, this criterion as applied here is not able to take into account this, and it is able it was possible to obtain a very good synthesis of the new result. Now in progress we have a different series with different reaxiality ratio and intermediate value of the phase angle. Also changes the geometry of the notch to see if the phase effect is not only tied to the material but also to the notch geometries. Finally, I would like to say that the main part of the results is reported in a review we have published with Professor Lazzarini in Material Science Engineering Art. And I would like to thank Professor Lazzarini for his contribution. Here I have some pictures from different conferences. I have reported the main people Professor Lazzarini meeting in his last conferences. I would like also to make his last sentence, because Professor Lazzarini was a great teacher and many of us have the luck to meet him. I think that this sentence represents which is the message of his teaching. To teach Latin to John, it is not enough to know Latin, it is also necessary to know John and love him. I have reported a picture with Professor Tovo. I think that the two most beautiful papers by Professor Lazzarini in 1996 and 1998 were written with Professor Tovo, and I would like to give this message to show you which is our estimation for this great man. Thank you.